But we will, of course, crack on with the presentation today, which is all about aquatic control engineering and how our solutions can help you have a low carbon outcome to your flood defense project, be that non-return valves, penstocks, flat valves, pumps, whatever. Yeah, so we're going to today be looking at reducing, not only from CO2 perspective, of course there's a lot of emphasis on CO2 at the moment, but also generally about the environmental impacts of the M&E equipment that we provide and others do as well, and how we can improve them, not just from a CO2 perspective, but all round improvement on sustainability and reducing the environmental impacts of these equipment. So, flood defences. Yeah, we all know that climate change is happening. Flooding is on the rise across the world. It's not just the UK, it's all across the world, and that's what I'm trying to show with this image here. You can see that from the 1950s to, well, this only shows the 2000, that the frequency of flooding in every continent has been on the rise. It's increasing everywhere. But also the weather is becoming more sporadic. We're getting almost the same volume of rain a year, but it's happening all at the same time. Now, what this means is our historic modelling for flood defence structures typically was always design a structure for a 1 in 100 year event. The problem is that now 1 in 100 year events are happening almost every other year, as you can see when I move to this slide. So this shows 3 recent floods. It doesn't include the flood that we've had earlier this year. So it's only 3, but these are all 1 in 100 year events, and you'll notice that there's not 100 years between them. This means, of course, that the structures we need to build need to get bigger, and the assets, as they get larger, their influence on everything from the environment, the ecosystem, the carbon outputs, everything will also increase. So a lot of people ask the question, well, why do we need to build these assets? Well, also, as you can see on your screen at the moment, there's a huge cost to not building these assets. These assets, they protect agriculture, businesses, transport, property, everything. You can see here how many billions is lost when a serious flood does happen. So you can see in 2007, the economic impact was 3.8 billion. That's a tremendous amount more money than's actually spent on building these assets in the first place every year. You can see, the impact in this blue, the lighter blue, is also towards business. Now, there's a fact that 1 in 4 businesses, statistically 40% of businesses that close due to flooding never reopen their doors. So it's not just the economic cost of losing those businesses, but also the potential that those businesses had. So from an economic perspective, it just makes sense to protect the businesses, the agriculture and properties and assets that this country has. The Environment Agency agree that the climate change is going to get worse. England flood planners must prepare for the worst. We're looking at rising sea levels. We're looking at higher temperatures, and therefore by 2100, we need to be spending at least 1 billion a year extra than what we are now on flood management. Andy, I've noticed a question has come in. I can't actually see the questions because of my view. So if you just stop me, is that okay when a question comes in?
Yeah, no problem, Martin. If anybody asks a question, I'll stop you and get it asked.
Yeah. Also, if anybody would like to ask a question, please do. We try and make these webinars as interactive as possible. So feel free to ask questions whenever something pops into your mind. So back to the presentation. What do these assets look like? Well, there's all sorts of assets to protect against flooding. Everything from large non-return valves or tidal valves, which you can see in the top left. There's pumping stations, that's in the top right. Of course, That's Keadby, where ACE are currently delivering 6 4 cubic meter per second pumps. We've got flood storage systems such as Morpeth, which is in the bottom right. So at Morpeth, we delivered the penstocks, well, the full M&E package actually. So penstocks, hydraulics, HPUs, control panel, everything mechanical, electrical on that one. But that is in a sense a flood storage dam. So when the water passing downstream increases above 100 cubic meters per second, the dam starts to close systematically. That protects the town of Morpeth downstream because they can't fit more than 100 cubic meters per second down the river, and creates a temporary reservoir upstream. So you've got assets such as that. Not everybody considers weirs to be a flood defence, but on one side or the other, they quite often are. Although they got put in usually for whether that be creating energy for textile production in the past, for example, or distilleries up in Scotland to tap water off. They've always been used as a source of energy. However, once they've been built and established, especially for a few hundred years, quite frequently you just can't remove them because the impact that the flooding could have downstream if you were to do so. So they become intricate and part of the river system, which unfortunately a lot of the time means that you can't get rid of these weirs anymore. So of course, building the structures in the first place has a lot of effect on the CO2 because the materials that we're using, they have to of course be mined, which quite often for steels, nickels that are in stainless steels, for example, iron, which is in steel and stainless steel, typically mechanical materials, they get mined in open cast mines, as you can see in the top right. It's not particularly great for the environment. You also have to move these materials all over the world. You've also got the production cost, turning material from an ore to usable product. That requires a lot of heat, also produces a lot of carbon. But you've also got the maintenance. And a lot of people, they miss the fact that the maintenance of a piece of equipment also requires a lot of combustion in terms of getting the engineers out to sites, particularly on flood defences where the sites are very remote. People have to travel there to look at it, to service it. And also with regards to pumping station and other movable assets, you've got the power consumption to actually operate it. So the power consumption used to rotate the pumps and pumping stations, but also move large sluice gates and things like that, all need to be considered. It's not just one part of the chain. You've got to look at the total cradle to grave of all of the products that we're working with. So one of the really big things that can help reduce CO2 is choosing the materials wisely, making material choices that enable you to reduce the amount of CO2 that we're releasing. So large considerations of your material choice when you're looking at it from a sustainability point of view is weight. The less it weighs, the less transport costs you have. The less it weighs, the smaller your lifting equipment can be. So for example, you could be able to get away with a small iron ferry crane rather than a large 50-ton crane if you're comparing lightweight materials to very heavy materials. The amount of CO2 released during manufacture, of course. Some materials, because of the amount of heat required in the manufacture, require a lot more energy, and therefore CO2 is released compared to other materials. You've got the longevity and the durability of the material. Of course, if one material produces 100 grams of carbon and another one 200 grams of carbon, but the 100 grams of carbon material lasts only an eighth of the time to the other one, the higher carbon material actually has the lowest CO2 impact. So the longevity, the durability is also a very important consideration. And then you've got the end of life. Is it recyclable? Can we do something else with the material, or will it go to landfill? If you can do something useful with the material, of course, that's far better and also helps reduce the impact on the environment. A really great way of showing what we're doing is the use of HDPE for a lot of our flow control equipment, particularly flat valves. So in the past, a lot of the flat valves, and to be honest, until really the early 2000s, when ACE was really starting to, we introduced the concept of the HDPE flat valve in 1995 to the UK market. But really, it was the early 2000s that it started to catch on as becoming the new normal for non-return devices. Before that, ever since the Victorians, it's always been cast iron, as you can see on the photo to the right. Yeah, so the material has huge amounts of benefits and vastly reduces the amount of CO2. I'll explain this looking at it starting from a weight perspective. So when you look at the weight of the materials, of course, that has a huge impact on the amount of CO2 that's released. As you can see, we're looking at the HDPE flap on the left, we've got a cast iron flap in the middle, and we've got a stainless steel flap on the right. This also starts to show you where the design has an impact, because actually most people assume immediately that the cast iron flap is going to be the heaviest. Usually on the larger sizes it really is, but on this particular size we're looking at 0.5 meter diameter. What happens is, because of the way that you have to fabricate either a mild steel or a stainless steel gate, you end up with this sort of flanged arrangement with the protruding pipe, and that actually makes it the heaviest of the three when looking at those options. Now, when you just look at the material of per ton, how much CO2 does it produce, you can see there's not a huge amount of difference between the HDPE and the cast iron. The HDPE produces 0.8 kilograms of carbon per ton, and the cast iron 1.26. However, because the HDPE is so much lighter, we're able to produce a lot more valves from a ton of HDPE than we would be able to from a ton of cast iron. So when you take the weight into consideration, you can see the HDPE is about 13 kilos for 0.5 meter. Cast iron, you're talking 65 kilos. Stainless steel and the carbon steel are up to 140 and a bit more kilos. Therefore, the overall CO2 per valve is vastly different from the HDPE only producing 10.4 grams of CO2 up to the worst offender, which is a pure stainless steel flap, which is nearly 1 kilo of CO2 per valve. So you can see enormous differences, and that's because the weight is so critical when looking at producing low CO2 outputs. Now remember, it's not just about the weight of the valve. The HDPE is lighter, so it saves CO2 on transport and the logistics getting it to site. Also, as I mentioned earlier, it could massively reduce the lifting equipment. I mean, when you're looking at this, 13 kilos, that's one man that can install that. 65 kilos, you're starting to have to consider possibly a very small excavator or operate a high-ab or something, because it's beyond the safe lift of 2 men. So lots of considerations. So it's not just about materials, as I said earlier. We've also got to look at intelligent design. Now, you saw with the flat valves the difference between the stainless steel design, just because with those materials you have to design it that way, and the HDPE, how much that has an influence on the weight and therefore carbon. There's a lot of different things you can do with design, and a really nice way to demonstrate this is with our Archimedean screw pumps. So our Archimedean screw pumps are different because they have a completely encompassed rotor which is sealed within the drum. So the whole drum rotates, the helix that goes throughout the drum is completely sealed, and what that means is that water cannot run back from the screw. Every drop that goes in comes out at the top. It's impossible for any run back to happen. Now, run back is something that's inherent with open trough Archimedean screws. You get a lot of water slipped back between the trough and the screw, which of course you need to pump up for a second time. So it reduces the efficiency. The other thing is, with an open trough, you can't pump into a head of water, because as a flood defense, even if you put a brake to stop the product becoming a hydro turbine, water would still slip between the screw and the static trough. So you'd always lose water or let water back into your drain. That means that with an open screw system, where the red arrow on your screen is where the bottom of the screw has to be. Now with our system, because it's enclosed, when the brake is applied to the shaft, there is no way for that water on the outfall level to slip back through the screw in the trough. This means we can reduce the overall height of the screw so that the output, or the bottom edge of the screw, can be where the green arrow is, underneath the red one. Now, on a Archimedean screw, this example is a 4 meters diameter. What that means is, as you can see with this figure here, that we can actually reduce the height of the overall pumping station by 2.751 meters when compared to a traditional type screw pump. That's massive. That's not just reducing the effective lift, therefore reducing the energy consumption. If this was a tidal pumping station, the overspill solution where you'd have a traditional screw tipping at the red arrow, of course, you're effectively pumping 2.7 meters extra height than you actually need to. So using a huge amount more energy than what you actually would need to. But it's not just the energy that's so clever about this. It's also, it shrinks the whole system. Of course, your pump needs to be less long because it's got less lift. The pump needs to be smaller, but the whole asset can be smaller. And when you know that concrete is one of the worst contributors to the production of CO2 or the creation of CO2, think about how much concrete you're able to lose when you're reducing the overall height of your asset by 2.7 meters. That is an enormous amount of concrete that we're saving just by really, really clever design. This is a nice example where we've built one. This is on the Isle of Sheppey, down in the Thames estuary. That's for the lower the lower Medway drainage board. So you can see these images here. On the left-hand side is the Archimedean screw, the kiosk being erected. ACE supplied not only the screw, but also the kiosk, the control panel, the non-return valves, and the stop logs. So we really did a nice turnkey project here. You can also see how it's lifted in, which once again helps because everything is modular. It's been made in the factory. It can be picked straight off the lorry, dropped straight into the civil structure. There's no grouting or on-site balancing of the screw that needs to be done, which means we can get rid of the crane quicker, also helping reduce the amount of carbon that we're putting out there. And then this is the overall finished product. So you can see it's a very neat, very tidy looking pumping station. So yeah, it's a project we're particularly proud of. Now, another big way you can save on carbon is actually by upgrading assets. On one side, there's a story to be told about if we use existing old assets for a long time, then of course, the longevity argument means that hopefully we use less CO2. Problem is, with a lot of aging assets, because of how old they are, they're not operating efficiently, they've not brought in newer technologies, and therefore they might actually be consuming fuels that are no longer desirable. For example, heavy oil, coal for a steam operated system. Believe it or not, there's some of those local to where we are that have only recently been switched out to electric. So upgrading assets can also have a really fantastic contribution to reducing that CO2 as well. This is a project at Appledore, which we delivered in the southeast. So you can see Dover over here to give you an idea, to get your bearings about where it is. And this is in the sort of Romney Marsh area of the southeast. So very flat-lying area, quite a few pumping stations down there. Now, this particular asset, until recently, still had a heavy oil single-cylinder Ruston engine. You can see what the engine looked like on the left. Unfortunately, that's not the actual engine. The engines were removed from the building by the time we got there. The pumps had failed completely, and they were using temporary pumps until the new pumps were ready. But that is a photo of what would have been there. It is the same model, same engine. So you can see it's a fixed speed engine. So it doesn't matter what levels the pumps are at, they could only operate at one speed. And of course, using quite a dirty fuel compared to well, electricity that we can now make from windmills, solar panels, yeah, you name it. I think we haven't used coal for almost, yeah, the past month or two. So we upgraded the asset. We removed the existing pumps were already removed. We then took out the pipe work so to enable us to install some new canisters where we can put some new, highly efficient, fish-friendly pumps on the front of the pumping station. Now, as I mentioned before, the existing motors and gearbox and setup meant that the pumps could only operate at one speed. Now, the new pumps are being operated through variable speed. So the pump will adjust its speed depending on the level difference, both upstream and downstream. So it's constantly measuring the intake depth and the outfall level and choosing the speed that is most efficient. In this case, they're trying to actually also keep a constant flow, which helps from a fish-friendly perspective, which is very important, but it also helps enormously towards producing a truly efficient pumping station. To explain this, it gets a bit technical now for a minute, but we've got two charts. So these are pump curves. This is typically issued with tenders or inquiries about a pump, so we can show you at what efficiency, what kilowatt usage, and everything the pump will require. But you can see the difference between a fixed speed and variable speed. So on the left-hand side, we've got fixed speed. Each one of these three graphs that you can see here, well, the top and the bottom one, this is slightly different, measure the efficiency, but they've only got one line, the bottom and the top. And that line represents one speed. At the bottom, we've got the flow, so the volume of water being pumped, and rising up the side, and the vertical axis is the head, so the head difference between the upstream and the downstream level. Now, what you can see is as the head difference decreases, the pump pumps a larger volume of water when it's fixed speed. And you can see as well, the energy usage drops off. So a lot of people think, well, the energy usage is less and my volume of water being pumped is increased. So what's the big problem? Like, surely that's getting quite efficient. But it's not the whole picture. Firstly, it's bad for fish because you get a lot of, well, towards the edge of the curve down here, you get high risks of cavitation. That's when small air bubbles start to explode on the impeller. The pump can start to rattle and things like that, none of which are good for increasing or maximizing the pump life. But the reality is the efficiency is also bad. You can see here, we're looking at trying to keep the pump, like Appledore, at a steady flow. So as the water level decreases, the head difference, the pump actually slows down. And that's why we've got these three lines. Each line represents a speed. So the top is the fastest speed, middle speed, and lowest speed. Now, that doesn't mean the pump can only operate at three speeds. It's fluid between these three. It's just to show on a chart, we pick particular points, which are a representation of different speeds. So it can operate anywhere in between here, but the pump is going to constantly try and operate at that exact same flow all the way through the different heads. Now you can see that there's a direct reduction of between 25 and 52%. So you can see the kilowatts drops off further when the pump slows down than it does when it speeds up. But of course you might say, well, yeah, but I'm pumping more water. So what if the kilowatts are double? Well, the reality is the relative reduction. So if you look at it from a kilowatt per cubic meter of water pumped, at this second point, there's actually a 14% efficiency benefit of slowing the pump down. And at this bottom point, we've got a 38% efficiency benefit. Now, a lot of pumping station, you actually pump on the lower flows more frequently than the upper flows. You've got to think that the pumping station has been designed for a flood situation, the worst case. That's where the duty points are quite often drawn up. The reality is you're actually often just taking the cream off the top, if you like, making sure the drain is maintained at that particular level. Frequently, this is being done at a lower volume, at a lower flow, so at the bottom end. So you actually end up spending more time pumping down here than you would do up there, which further means that the energy savings through these variable speed drives are absolutely enormous. So the outcome of upgrading an asset such as Appledore is no more diesel being consumed. We've got clean electric station now. It's proven and rigorously monitored by a fish-friendly impeller. So from a fisheries perspective, so also looking at the environment as a whole, it's improved. Less efficiency loss. The system's not getting really hot as you would do from an old diesel-operated thing, which is producing lots of heat and getting lots of mechanical loss through the gearboxes and the drive shafts and everything else that's on there. As I explained, the variable speed drive, huge benefits on there. Now, also using new technology, we did a lot of work with CFD, that's computational fluid dynamics, to make sure the flow was presented to the pump in a way that was going to allow it to run through the system as efficiently as possible. So we can do that, which back when Appledore was built, wasn't possible because they didn't even have computers. We expect, now it's very difficult to be super accurate because we don't have all of the existing technology figures and pump heads from the past. A lot of them have been lost, but we expect an improvement of at least 30% from an efficiency perspective, probably somewhat more. And then, as I explained earlier, it's also the maintenance. Now, as everyone knows, these old motors require a lot of maintenance. They require love and care to keep them operating and chugging along. Electric pumps aren't like that. They're fit and forget for a few years. You can't forget them completely, but very little maintenance is required, which means less traveling to site, less going to and from, saving fuel and mileage for the Environment Agency. Now, our pumping systems allow us to do something else which we're really excited about, and we're hoping that we can start finding some projects where we can embrace this technology. Of course, you, our customer base, are the people that have to say, I've got a site which I think we can do this with, but it's definitely a technology which is available. It's carbon neutral pumping stations. Now, a lot of pumping stations, particularly pumping stations that allow water to drain into the sea, so they're the final terminal outfall, if you like, or the pumping station on the coast, which is the ultimate, the final pump before the water's expelled out into the sea. A lot of the time, they're not actually pumping. They're operating through gravity. So most of them have one or two or several gravity sluices, and they try and, at low tide, let as much water out to the sea as possible through the sluice. Of course, it's completely free. You don't require energy. Makes complete and utter sense to only pump when you need to pump because either there's a high tide and you've got too much water in your drain or whatever the circumstances might be. But while the tide is low, get rid of that water as much as possible. Of course, there's a lot of kinetic energy in that water. So what if we could harvest that? What if we could let the water go out to sea and it rotate the pump, allowing the pump to actually generate energy? Now, this is what you're looking at right here. So this is a horizontal pump. So it's been installed, as you can see, horizontal. This is submersible, so it's a submersible motor. So this whole cavity here could be filled with water. And the water is pumped or drained this direction through the valve. So you can see the windscreen cleaner at the inlet, it runs through the pump, out through the non-return valve. There's an emergency penstock out here and into the sea. Now, this particular one, which was built in the Netherlands, unfortunately doesn't run out to the sea. It runs out into Lake IJsselmeer. It controls level between two. However, it can actually function the opposite way around. So sometimes they open up the penstock and you'll see from the flap valve that it's actually rising flap valve. So it can lift out of the way and sometimes let the IJsselmeer water back through the system. So that's another benefit of horizontal pumping. You can see the construction of the whole pumping station is very low. So from an aesthetic point of view, you've not got a big eyesore out there. You've not got a big tall building that everybody can see. You can keep everything low, hidden in the environment, discreet, and therefore, people quite like it. This is the pictures of the construction phase of this particular project. Each of these pumps was about 4 cumex, so 4 tons of water per second per unit. You can also see how there's a very clever installation technique being used here. You've got this galvanized puddle flange, as you can see on the edge here, on the front and back. So how it's installed is the pump is lowered into its position, and the wall is cast around the puddle flange at the top and bottom. So you're actually using the pump itself as a jig, and because of that, you know it's going to fit precisely. Once it's installed, the bolts between the jig and the puddle flange, or the pump and the puddle flange, are removed, and then you can simply lift the pump in and out whenever you wish. You don't even need to go in. You just need to attach the lifting tackle to the top of the pump, and it seals using its own weight. So very easy to maintain, very easy to look at, very easy to install. It's a really, really smart system. So how it generates energy, of course, is when you're pumping from your drain side, where it says NWL on the left-hand side. You're pumping through the pump, consuming electricity into your tidal side, which is higher than your drain side. Now, when the tide drops out and you're able to use gravity, you can, of course, just let the water run from the drain through the impeller and into the sea. When it's doing this, it actually will turn the impeller. Now, with our permanent magnet drives that we use in our pumps, they become very, very efficient generators. So you can actually generate power. And the idea is to at least carbon offset the pumping station, but on particular sites where you've got particularly high heads, tidal heads, there's no reason why you couldn't have a completely carbon neutral pumping station, possibly even a carbon negative pumping station. So really exciting technology, one that we're really, really keen to look at for the UK, particularly as the UK has so much tidal range all over its coastlines. I think it's an exciting concept. Could be an interesting part of the energy mix. Now, another thing that we're working with some of our partners, this is with...
Hi, Martin.
Yeah?
Just a quick question coming around pumps before you move on.
Okay.
Someone asking about maintenance packages. Do we provide them? And how often do our pumps need to be serviced? And would we do that service for them?
We certainly can provide maintenance packages. It depends in terms of cost, what type of pump, whether it's an Archimedean screw or an axial flow. Also, of course, the location is important to us because we're based in Lincolnshire. So, of course, if the pump was in the north of Scotland, yeah, it's going to get a little bit more expensive because we have to travel. But it's certainly something we can look at and something we can offer with our pumps.
Thanks, Martin.
Cheers. So as I was saying, one of our partners who makes the large gates with us, Janssen Veneboer, is also exploring biotechnologies, so biodegradable materials. And what can we possibly do with this? Now, I will be open with you. We are in the early stages of this, but it's a field that's opening up lots of potential avenues, really interesting developments going on. At the moment, there's been a bridge that has been built fully, so not the concrete supports, of course, but the actual bridge deck, the sides, the whole lattice work, the hand railings, all of that bridge deck and this static deck that's on this side has been made out of flax. So flax is, of course, flaxseed. It's also being used to make linen in shirts. Looks like this. That's being used with a biodegradable resin, which then sets. Now, it's at the moment it's an 85% biodegradable resin, but they're looking at that as well to see if they can make it even more biodegradable. And then being used in molds, much as a GRP or carbon fiber would be, to produce bridge decks. So this is a picture of the bridge. It's a cycling bridge up in Friesland, so northeast Holland. It's the first biodegradable bridge in the world. Now, a lot of people would think, well, yeah, if it's going to biodegrade, it's not going to be great for a bridge because it's just going to rot and then it will turn into a sort of compost whilst people want to cycle over it. But there is, of course, very special coatings, and much like cardboard would not degrade if you keep it in a dry environment, this material won't degrade whilst you're keeping it dry. So as long as you've got good coating systems to prevent the weather from really getting into the material, then it will and should last a long time. Now, this particular, you can see on this slide how it moves. It's a swing bridge. So this particular bridge is one of the first of its kind. There's some universities involved with the project, and the bridge is laden with sensors. So they've got over 1,000 sensors in the bridge at the moment, monitoring the flex, the movement, any deterioration in the materials. Is being sponsored by the Dutch government, because of course they're looking at becoming more environmentally friendly and conscious as a nation. So they need to also have their input into the bridge and look at the materials. Now, Jans Venneber, our partners, do build movable bridges, but of course, as I said before, they also build large sluice gates for us. We've just delivered a massive set of stop logs in Ireland, which was 12.5 meters wide, 6 meters high in Dublin in steel. But they are looking at, can we possibly in the future take these materials? Can we use them in water? There's big question marks, but that might be possible. If not, what other kind of biodegradable materials? It's all about using that innovation and pushing forward and trying to find really clever ways of delivering what used to be very CO2 and environmentally negative impact kind of assets and architecture and structures, and trying to make them as clean and green as we possibly can. So that's the swing bridge. That's it's now complete, fully open. If you go to Friesland in the Netherlands, you can go and cycle over it. Yeah, really nice project. So this presentation is a bit shorter than the usual. Of course, it's looking and exploring what we can offer from a carbon reduction point of view. I hope you found it interesting. And before I go, I will ask Andy, are there any more questions?
No, that's it, Martin.
Okay, if you've got any questions, I'll give you another 20 seconds or so to get them asked. But otherwise, I hope you enjoyed that, and you can see what ACE are doing and how much effort, but not ACE on its own, but also ACE with our partners are putting into really providing sustainable solutions for the future. Is there any questions, Andy, or is that a wrap?
No, that's a wrap, mate. Thank you.
Great. Thanks a lot for attending. Cheers. Bye.
Bye.